So what we're going to do now is continue with chapter 19 and focus specifically on the chemistry of acid anhydrides. Okay, so I will zoom in just in this ChemDraw so we can see sort of where we're starting from. Here is an anhydride, a compound that looks like this. Again, that's characterized by having a carbonyl, oxygen, another carbonyl. That's the characteristic anhydride group. And in general, like we talked about with the reactivity of the acid chlorides, the way we make acid anhydrides is by doing a nucleophilic substitution reaction, taking a carboxylate anion. Okay, so that's this guy here. This is my carboxylate anion. It acts as a nucleophile, attacks the electrophilic carbon of the acid chloride. You then form a tetrahedral intermediate that collapses back to kick off the chloride and generate the desired anhydride product. Again, this is the nucleophile. It attacks the electrophilic carbon of the carbonyl, tetrahedral intermediate, kick off the chloride, reform the carbonyl, generate the desired anhydride product. And when we talk, so that's how you make the anhydrides. When we talk about how the anhydrides react, fundamentally they react similar to acid chlorides, however they're a little bit less reactive than the acid chlorides. So in general, all of their reactivity is going to be just a little bit slower. So the first reaction of the acid anhydrides that we're going to talk about is what I'm showing here is reaction 10. That's hydrolysis of the acid anhydrides. The overall reaction is I take an anhydride, treat it with water, and form the carboxylic acid. The mechanism is similar to the mechanism of pretty much every carboxylic acid derivative that we've covered until now, which is that this oxygen the water comes, forms a tetrahedral intermediate over here. We're going to collapse back that tetrahedral intermediate and kick off, in this case, a leaving group that is the whole carboxylate anion. So now this whole part of the molecule here now becomes the leaving group with respect to this carbon of the tetrahedral intermediate. So again, this water was the incoming nucleophile. I have an anion tetrahedral intermediate. I reform that carbonyl, kick off the carboxylate anion, which is my leaving group for this particular tetrahedral intermediate. And now what I have is a carboxylate anion. That's the leaving group that got kicked off. I also have a protonated version of the carboxylic acid product. I can now do a proton transfer, so this O- will pick off a proton, neutralize that positive charge, and form as a product two equivalents of this carboxylic acid. Now if I had an unsymmetrical anhydride, meaning if these R groups were not the same, what I would get is two different carboxylic acids. Here, because my anhydride is symmetrical, that means both R groups are the same, I end up getting two equivalents of this carboxylic acid as a product. But again, the mechanism here is exactly the same as the mechanism of every nucleophilic acyl substitution reaction that we've been covering until this point. Again, you form the tetrahedral intermediate, collapse, kick off a leaving group, neutralize the charges, and call it a day. Reaction 11 that we're going to discuss in this video is the alcoholysis of anhydride. So forming an ester by treating an anhydride, in this case this guy here, with an alcohol. And this is catalyzed by base. And overall, this reaction, you start with an alcohol in this case, you treat it with an anhydride, what you form as your product is an ester over here, and the rest of the anhydride, the part that did not go and become attached to the alcohol, becomes a carboxylate anion. So let's go through the mechanism. Again, this is not going to surprise you. Hopefully this will not surprise you. The first step is to form an O-, this is a phenoxide in this case, anion, by treating the alcohol with the base. This is a great nucleophile. It will attack this carbonyl, push up the electrons, form this tetrahedral intermediate. Again, the collapse of anhydride tetrahedral intermediates always kicks off a carboxylate leaving group. Just like in the acid chloride reactions, we always kicked off a chloride leaving group. Here in the acid anhydride reactions, we're always kicking off an anhydride carboxylate leaving group. I reform the carbonyl, kick off the carboxylate leaving group. That has the effect of generating this ester product as well as a carboxylate anion. And again, hopefully none of this is surprising to you. since we're starting to see the same reactivity patterns appear over and over. I can also take an anhydride and undergo aminolysis, which is effectively forming an amide starting from the anhydride. And the way I do that is what I'm showing over here, where I start with this NH2 group, I treat it with an anhydride, base catalyzed conditions, and generate this product shown here, this amide. For this particular substrate, the reaction occurs only at the NH2, and that's because it is more nucleophilic than the OH group. So here this OH group is going to be essentially untouched in the presence of these reaction conditions because it is less nucleophilic than the corresponding NH2. The mechanism for this reaction, once again, NH2 nucleophilically attacks, kick it up, tetrahedral intermediate. Alright, this tetrahedral intermediate collapses, kick off carboxylate. Here's my leaving group from anhydride reactions. Here's my protonated amide product. And this protonated amide product, after treatment with a base, will give me my desired final amide product. So again, just to review on the anhydride reactions, I make anhydrides by reacting a carboxylate with an acid chloride. This is how I make the anhydrides. I can react those anhydrides either with a hydrolysis, alcoholysis, or aminolysis reaction to form carboxylic acids or esters or amides. We're going to move on now to talk about the chemistry of esters. And the way that we make esters, this is pretty much a review, so we've done all of these reactions before. One option for making an ester is to start with the carboxylic acid, treat that with a base to form a carboxylate nucleophile, and then treat that now with an alkyl halide to form an ester. This will work if the alkyl halide is primary, which means therefore that it is not too substituted to undergo an SN2 attack, because that's effectively, this is an SN2 reaction mechanism shown here. And this will work again for primary alkyl halides. I can also take a carboxylic acid and treat it with an alcohol under acid catalysis to do a Fischer esterification. This generally works for simple alcohols, simple or unhindered alcohols. What I can also do is do esterification sort of more generally starting from the acid chlorides, because of those guys are so much more reactive than the corresponding carboxylic acids. Pretty much any alcohol and then the pyridine base that I put in will generate the desired ester sort of very generally without so much of issues as we have with the less reactive carboxylic acids. Again, just to remind ourselves, these esterification reactions tend to be sensitive to sterics in the sense that we can get selectivity for less sterically hindered alcohols over more sterically hindered ones. On the other hand, the steric bulk around the alcohols generally does not prevent them from being able to react pretty much wherever they would like. Now when we talk about, so that's how we make the esters. When we talk about reacting the esters, for the most part, they react similarly to the acid chlorides and the acid anhydrides, but these now are less reactive than both the chlorides and the anhydrides, and they can undergo hydrolysis or aminolysis or reduction. Those are our three choices here in this case. Yeah, or Grignard reaction. Okay. So what do these esters do? They can undergo hydrolysis. They can undergo hydrolysis to the corresponding acids, either under acid catalysis or under base catalyzed conditions. The acid catalyzed mechanism is pretty straightforward. Here I take a carbonyl, it finds a proton, it gets protonated. That's my first step. The water will come and do nucleophilic attack, form this tetrahedral intermediate. Now again, let's remind ourselves, we need to kick off the OR prime group, the alkoxide, but we're not going to want to generate a negative charge under acidic conditions. So first step will be a proton transfer of this H onto this OR. Then I can collapse back to form the desired free acid and kick off the alcohol as my leaving group. Here R prime OH is going to be my leaving group now for this reaction. Neutral alcohol. And again, by using water to pull off this proton, I regenerate my acid catalyst and now form the neutral carbonyl product. I can do base catalyzed ester hydrolysis. That's also called saponification. So that's the reaction shown here. This mechanism is pretty straightforward. OH minus acts as a nucleophile, push up the electrons, I form this intermediate, collapse back, kick off alkoxide. I now, in two simple mechanistic steps, have my carboxylic acid as well as the alkoxide. And in this particular case, and the alkoxide in that case was the leading group, in this particular case, what I will be able to do now is take an OH minus and pull off a proton from this carboxylic acid to generate, as sort of my final existing species here, a carboxylate anion product. Okay, so again, I can hydrolyze those esters back to the carboxylic acids, and I can do that using acid catalyzed conditions, sort of the same mechanism that we've been talking about until now, or I can do base catalyzed saponification conditions. These esters can also undergo aminolysis to form amides. Alright, so here's a sample reaction. I take this ester, treat it with ammonia, form the amide plus this CH3OH, the methanol now leaving group. The reaction mechanism for this is, first the ammonia will come, attack, nucleophilically attack, push up, tetrahedral intermediate, collapses back. Now in this initial step here, what I'm going to have is an NH3 plus and a methoxide anion. However, we can do a proton transfer between those two molecules to now give us the desired product. So again, these are my initial products, this protonated amide as well as the methoxide. But if I proton transfer this proton from the amide to the alkoxide, I will form my desired neutral products in this case. I can also do a reduction of esters. Alright, so if I take an ester and I treat it with lithium aluminum hydride followed by acid, I am going to form the primary alcohol, analogous to all cases of carboxylic acid derivative reductions. Again, the LiAlH4 is a good H- source. I will also form the alcohol as a byproduct for this reaction. And again, this is the same mechanism. So the H- source will come in and do a nucleophilic attack. Alright, my first product, my initial product, is going to be an aldehyde. However, that aldehyde is going to be even more reactive to the H- than my initial ester is, in which case it is going to rapidly undergo further reduction to give me again the primary alcohol product. For esters, I have another option, which is sort of something that hasn't been available for my other carboxylic acid derivatives, which is that I can do these reactions and figure out a way to stop the reaction at the aldehyde stage. In this particular case, I use what is called dibol or DIBAH, okay? DIBAH. This is diisobutyl aluminum hydride. The structure of that is shown here. If I take this ester, for example, treat it with the diisobutyl aluminum hydride followed by aqueous acid, I will form the aldehyde only, and this will not undergo any further reduction to the primary alcohol product. Now, what esters can also do, which is kind of interesting, is they can undergo reactions with Grignard reagents, analogous to the reaction of a acid chloride, for example, with a Grignard reagent, and the product of these ester reactions will be a tertiary alcohol with two identical substituents. Okay, so here, like with the acid chlorides, this Grignard reagent will add. I'll form an initial ketone that's going to react further to give me now the tertiary alcohol, again with two identical things attached to it. Okay, so this is a little bit confusing because they're all the same in this particular case, so let's just be clear on this. I can change this example to do this now in a way that's hopefully less confusing for you. So if I take now two equivalents of a Grignard, of methyl Grignard, and react that now with this ester, I'm going to form this tertiary alcohol product where I have two methyls. They came from the Grignard. The phenyl group attached to this carbon, what was the carbonyl carbon, was in the initial starting material, and I also will kick out now methanol as a leaving group. So that's the ester. Again, we make the esters. Let's just review the esters 1 second. I can make the esters by SN2 substitution, by Fischer esterification, or by alcoholysis of a acid chloride. Once the esters are formed, they can undergo hydrolysis under acid or base conditions. They can undergo aminolysis to form amides. They can undergo reductions or partial reductions, for example, and they can also undergo Grignard addition reactions. So esters are really versatile intermediates. I can also now move on to talk about the chemistry of amides in this case, and I can make amides. Let's just review where we are on the amide synthesis. I can make amides from the corresponding acid chlorides by treating it with ammonia to form a primary amide, but with this guy here to form a secondary amide, or with a disubstituted amino compound to form a tertiary amide product. The mechanisms of all of this are what we talked about in class with the acid chloride chemistry, so we're not going to go through it here. But again, this is the most general way to make these amides. What reactions do amides undergo? Well, we're going to just do two reactions of amides in this case. The first is that they can undergo hydrolysis, and then hydrolysis can be, again, either acid or base catalyzed, although in this case it's a pretty strong preference for doing acid catalysis, and the reason for that I will get into in a second. The acid mechanism shown here: protonate this carbonyl oxygen, nucleophilic attack of the water molecule, proton transfer from that tetrahedral intermediate, kicking off of the ammonia leaving group. Hold on, why does it say NH4+? I think it's just NH3. Good, sorry guys, NH3. Kick off ammonia, regenerate the acid catalyst to form the neutral carboxylic acid. The base catalyzed mechanism, which is what I am showing here, involves an OH minus attacking. You form a tetrahedral intermediate, you collapse that, kick off NH2 minus to give me my product. Now the reason this reaction is so much more difficult than the acid catalyzed hydrolysis is because NH2 minus turns out to be a lousy leaving group. That's a terrible leaving group, which is why in general if you want to hydrolyze an amide to a carboxylic acid, you are going to have a strong preference for doing the acid catalyzed rather than the base catalyzed reaction conditions. Okay. Now, finally, when we talk about amide reactions, amides can also react with lithium aluminum hydride. However, in this case, instead of forming primary alcohols like we have for most of the other carboxylic acid derivatives, this is pretty interesting. We have we form a primary amine compound. Okay, so what we're ending up doing in this mechanism, and if you are interested, although you will not be held responsible for this mechanism, you can go through the book, which we'll discuss it in detail. And that effect here is the conversion of a CO, of a carbonyl double bond, to a CH2 group. All right, and that involves expelling the oxygen anion as a leaving group. In this case, the anion is coordinated to aluminum, so it makes it a more happier leaving group. But again, you're not responsible for the mechanism. However, you are responsible for knowing that an amide like this can be converted to a primary amine by reacting it with lithium aluminum hydride. So we have less reactions for amides because they are substantially less reactive than the other carboxylic acid derivatives. But what they can do is they can undergo, again, hydrolysis or reduction, and those are going to be sort of where we end chapter 21 as far as what you are responsible for knowing about.